Hello, my name is Matthew Newland, and in this video, for homework assignment 4, we are going to be deriving the heat diffusion equation for Cartesian coordinates. So, to begin, we're going to start with a cube with a certain material to it. So, we're going to come over here, and we're going to draw out our cube. So, we are going to come over here, draw out a cube. And at least for this particular equation, we are going to have our directions kind of placed in a kind of weird orientation. So we're going to come over here and draw our coordinates. So going up, we're going to have our z value going into the page is going to be our y value, and coming out like this is just going to be our normal x value. So to start by deriving our heat diffusion equation, we can just start what's going in and what's going out. So we have heat going in and heat going out for every single direction. So we're just going to draw that. We're just going to label and draw that out now. So we have our heat going in, which is going to be represented by Qx. Going into this surface, we have our heat going in through the z direction, which is going to be coming into the page, or coming up, so it's going to be from this angle. So it's going to be Qz, and that's going to be going up like this. And then we also have Qy, which is going to be going into the page like that. And now we need to find what's going out. So what's going out? It's going to be our heat going out, so it's going to be Qx plus dx, the change plus the change in position. And then we can also say that for the rest of our directions. So we're going to have our heat going out in the z direction, the change in position. So it's going to be Qz plus dz, and then we also have our heat of the y value going out in change with its change in position. So we're going to draw that out as such, and that's going to be Qy plus dy with its change in position. So starting from here, we can then derive, or we know what's going out and what's going in, and we can then start from here, and then we can start expanding our equation out in order to find what each of these variables is going to be. So we're going to go over here and we're going to find out what's going out. So what's going out in each of the directions? Luckily, we only really need to find one in order to find all of them, because they all follow a particular path for this cube. So we're just going to start with our x value. So our heat going out with its change in x, with change in its position in x, is going to be the heat going in plus the change in the heat flow with respect to its position multiplied by position x, by the change in position of x. And then we can just write that out for the rest of our directions, except replacing this x with y and z. So we're going to have Qy plus dy is equal to Qy plus our heat flow of y times our change in y times its position, or change in position of y. And we also have our z, so it's going to be Qz plus dz is equal to heat flow in z plus its change in QZ over its change in Z times its change in position of Z. And why I'm labeling these two separate variables or derivatives as sort of that weird hook D, because this would represent what is it? It's not a cross product, but it's a partial differential equation. And this this equation comes from a Taylor series expansion, but we're not going to be doing that because this would take way too long if we had to start from our Taylor series expansion. So we're just going to start from here. So why is this important in terms of this? So we're going to look at the units of this sort of other half of the equation. So this other half, we're just going to represent this other half by our change in Q naught over our change in naught multiplied by our change in position of naught. What does this mean? This means that the change in heat flow can change with position. And that's multiplied by the change in position itself. And what this means, just summarizing in layman terms, is that the heat flow, while it's going throughout this cube, no matter what direction, it's not going to be constant. So we have to represent that before we go even farther in this equation. We got to represent that because this could be any material, and that heat flow could be affected by the properties of that material. So we have to state that the heat flow is not constant, and it's changing as it's traveling throughout this cube in any direction. So now we have this value here. We're going to sort of branch off and start looking at this in terms of energy, because when you have heat in a system, there's going to be some energy going in, generated, stored, and then energy going out. So we're going to find our energy storage equation. So our energy storage equation is going to be the energy going in plus the energy being generated. And what energy being generated means is that this is kind of just assuming that there's a reaction or or either nuclear reaction or electrical like energy being applied in sort of the center or the inside of this cube. And so we're just going to represent that as our energy generation. And then we have our two positive values, which is the heat going, or our energy going in, plus the energy being generated, minus the energy going out, is equal to our energy storage. And then we also got to represent of how much energy is being stored due to this process. So we're also going to write energy storage. Like that. And these two are where we are going to build our fundamental heat diffusion equation. So going through each of these terms, we can then sort of expand that out a little bit in order to get a very long equation that's going to take all of these terms together. So what we can say already is that our heat going out, our heat going in, and our heat going out is represented or our energy going in, our energy going out, excuse me, is already represented by the heat going in and the heat leaving. And we can immediately roll those two, we can immediately find formulas for those two equations. So we're gonna come over here and then write them out for you. So our energy going in is equal to our heat going into the x, our heat going into the y, and our heat going in at position z. And then our energy going out is going to be I'm going to put a negative there just so I don't have to write out this huge equation before we even get to the really long one. So it's the negative of our heat leaving, our heat plus at position, our heat flow at position at the position of dx, which is how far our x or y or z is going to expand, how far it is going to expand. So it's going to be plus qy plus dy plus qz plus dz. And now we have two kind of weird terms that we don't know how to represent just yet. Is what is the energy generation being generated in this cube, and then how much energy is being stored because of all the rest of our variables here. So what can we say? Well, let's just start with our energy generation. So our energy generation is our volumetric heat flow in terms of our volume. And we very much need, and since our Q dot here is already in units of volume, so we need to make sure we have those units cancel out with dx multiplied dy times dz. Sorry, let me get an eraser over here. And now with all these terms we can find our energy stored. Energy stored. So what is our energy stored? So energy stored is going to be based upon the temperature of this cube and how much our cube is going to kind of resist that change a little bit. So we need to know both the density and the heat capacity in terms of our volumetric units. So we're going to state exactly what I just said. So it's going to be density times heat capacity times the change in temperature with respect to time, and then we need to take this in our volumetric units. Kind of the same way we did in our energy generation. And kind of just to express this again, we're going to come up here and we're going to say that that unit down here is going to be our density times our heat capacity times our change in temperature or change in time. And this is going to be our what is it? This is going to be the volumetric or volumetric heat storage in terms of our and before we multiply our volume out. So we're gonna come over here, and then we're gonna come down here, and then start trying to expand this equation. Just to box this, just to show that these sets of equations are very important here. So we have kind of two equations, then we can start trying to expand a little bit. So we're gonna start with our energy storage equation, and then set it equal to the one we have down here. So we're gonna come over here and say that our energy in plus our energy generated minus our energy out is equal to our equation from down here. So it's going to be our density times our heat capacity times our change in temperature with respect to the change in time multiplied by dx, dy, and dz. And then we're going to plug the rest of our equations here and then have it set up where we can start trying to expand this out even farther with the rest of what we got. So we're going to come here and say that our energy in is going to be equal to our heat from x plus our heat from y plus our heat from z plus our energy generation here, which is going to be our heat flow in our volumetric units, so it's going to be dx, dy, dz, and then it's going to be our energy going out. So it's going to be qx plus dx minus our q, y plus dx minus q, z, dz. Oh, I messed up right there. That meant to be that. I meant to say dy, not dx. And then that's going to be equal to our right side of the equation. So it's going to be density, heat capacity, times our temperature, times our temperature with respect to time with our volumetric units. And with this, we can then we can start to expand our equations even farther. Starting back from here, one thing I want to correct in the previous video is that I said that it was the heat storage, it was that this portion here of our heat storage equation was, of our energy storage equation, excuse me, still got that wrong, was heat storage. That's not correct. The actual correct response is the energy of the medium per unit volume. And that's where our units from our volume here cancel out to make our heat storage equation. So that's why I wanted to sort of write this out and keep it here to make sure I clarified that, because I don't want to get that wrong. So going back to this equation, we can then substitute all of our formulas from here into our formula here, and if you notice, is that we have a qx, a qy, and a qz all in here, which then will cancel out with our qx, qy, and qz. So from here, we can then say this. So we're going to have we're just going to substitute everything in. So we have only this half of the equation only being operated on now. So we're going to go over here and say, start with our x's and our y's and our z's. So we have our change in the heat flow with respect to x over dx, multiplied by dx. Then we have our y value and then we still have our heat generation equation. So what do we do from here? What do we do from here at this point? Because what we can do next is try to get rid of these dx's, dy's, and dz's. But then we're going to be stuck with a whole lot of math to do in order to get them out. So we need to bring in another property to expand this equation out even more to get to our final heat diffusion equation. And the main property or law we're going to be doing that is going to be from Fourier's law. And what that means is that it's the it's the what Fourier's law represents. It is the heat conductivity rate for an isotropic material, which means is that heat conductive rate is going to be the same throughout the entire material, no matter what direction you're going. So we're just going to write down Fourier's law and then figure out how that's going to interact with our huge equation over here. So so what is Fourier's law? In terms of our equation, we say that Fourier's law is going to be equal to Qx is equal to negative K, which is heat conductivity, and then it's going to be dy dz multiplied by dt over our change in temperature over our change in time. And if you notice is that we're missing, not our change in time, excuse me, our change in x. So our temperature and change in position. And one thing from here is that it's very, very similar to our heat flux equation. And what heat flux and how we find Q our heat coming in from X is actually, draw an arrow. Our heat flow coming from X is the heat flux of X multiplied by the area. And you might be thinking, area? We don't have parameters. We do actually. We're just expressing it in a different way. Technically, dy and dz are technically area is going to be our area because it's the change in y and the change in z, or the change in position of y and z, which then we can find an area from. So we're going to come over here and then write out the rest of our Fourier's law equation. So it's going to be qy is equal to negative k dx dz, and oops, sorry, let me get my eraser. And then we're going to go on to our z value. And all these have their same heat flux equation. It's just going to be the same, except that this x value is just going to replace what it's trying to find. So this is going to be our q and y is going to be equal to our heat flux in y times our area, and then it's going to be our heat flow in z equal to our heat flux in z times the area. And this is our Fourier's law. And from here, all we have to do now, instead of just substituting, and besides substituting, because we have to substitute Fourier's law in, is just basic algebra and trying to find how these derivatives will cancel out. So we're gonna kind of do a couple steps at the same time here. So the first thing we're gonna do is substitute our Fourier's law equation into our equation up here. And you might be wondering, how are we going to do that? We don't have a Qx, a Qy, and a Qz all by itself. However, we kind of do. It's because we have a Qx, a Qy, and a Qz all in this equation, but it's getting multiplied by that derivative variable with respect to its change in position. So what we can do there is kind of spread that out, but instead of just stopping there, because we're going to have an entirely messy equation, instead of writing that entire mess out, we can immediately tell that we have a dy and dz, a dx, a dz, and a dx, dy. Sorry, I kind of drew that a little weird. That's a dx, dy. And we also have a dx, dy, dz in all of these. So what that means is that the dy dx variables are going to get canceled out when we divide both sides of this equation by our volumetric units. So I'm going to write that a little better. Our volumetric units. And then we're going to have a new equation as such. So we're going to come over here, kind of just pull all of that this derivative in regards to its position, just out of it. For the time being, just to make it a little easier to read. So this is now the new term here, after dividing it by our volumetric units, and also placing in our Fourier's law equation. And then we're going to come over here and do the same thing for the rest of our variables. So it's going to be dy over k times our change in temperature, our change in position, plus the derivative of dz times k times our change in temperature in regards to position of z. And then we're going to come over here, and since this had the entirety of the volumetric units, it's just going to be Q dot, which is going to be our heat flow, our heat flow. And then on our right side of the equation, that volumetric units are gone, so it's just going to be our density times our heat capacity times our change in temperature times our change in time. And now what we can do from here is that what we're going to do next is actually divide both sides of this equation by K, this thermal conductivity, because at least we're just going to say for the time being that this thermal conductivity is actually just a constant. And then we can divide both sides of the equation by our thermal conductivity, because technically there's another equation that we can use here, or another property that we can use, where it's an alpha value, and it involves our density, and our heat capacity, along with K. So we can then substitute that in and try to figure out how this mysterious alpha value is going to substitute into our equation. So we're going to divide everything out. Excuse me. We're going to divide everything out, and then just take the next derivative. So we're going to have so it's going to be d squared t, and then it's going to be dx squared plus d squared, our second derivative of the position of y, plus our second derivative of the temperature with respect to z, plus our heat flow divided by Q, which is going to be equal to the density times the heat capacity divided by K. So I'm just going to make that a subscript. And then I'm going to divide that by our change in temperature with our change in time. And then now we're going to move on to that alpha value I was talking about earlier. So that alpha value is going to be, alpha is going to be equal to K over our density times heat capacity. So if you tell, it's just flipped. So we can come over here and say that 1 over alpha is just equal to our density times heat capacity over our thermal conductivity. And so we're going to write an actual final equation for this now. So our final heat diffusion equation is going to be as such. Is then going to be, oh, sorry, I kind of made a little mess there. a little mess. And then we say that our new right side of the equation is going to be that substituted alpha value in times our change in temperature times our change in time. And this is going to be our final heat diffusion equation. That is going to be our final heat diffusion equation. And the good thing about this is that with this, we have our sort of time sensitive, our time derivative on one side and our position derivative on the other. And that is good because that's keeping our position and our time separate. And we can then technically find how it's going to change we can technically solve different problems by either leaving out certain second derivatives or putting them in. So if we were just trying to find a unidirectional problem and see how the heat flow was just going to go in the x value, then we would only need this second derivative of x, and we wouldn't need either of these. And if we said that this was also in steady state, we wouldn't need this heat flow either. And then we could have a new equation where it's just the second derivative of the temperature with respect to the position of x is equal to 1 over the alpha value multiplied by our change in temperature and our change in time. And that's the beauty of this equation, because we can then kind of just separate everything off into its individual components from here.